Welcome, friends. So, we have discussed the very brief idea about resistance, inductance, capacitance, and thereon we have discussed, or we have defined, or we have introduced some terms relating to the network, like independent, dependent source, supernode, supermains, and so on. Now, in this part of this lecture, we shall discuss few problems, numerical problems on resistance, inductance, and capacitance. So let us consider our first problem. Let us consider figure 14. So we have a very complex structure, complex network containing several resistances are there. Now it is to be find, that is, what is the resistance with respect to AB terminal. So we have 1 ohm resistor, we have 5 ohm resistor, we have 6 ohm resistor, so on. So lot of resistances are there. So we need to find out a resistance with respect to AB. So that means, now if you want to replace all these resistance with respect to a single resistance, that is equivalent resistance, what will be the value of that resistance? That is the problem is all about. Now the problem can be solved by the knowledge of series combination and parallel combination of that resistance. Now let us first name these nodes. Actually, see, let us name this node is P, this node is Q, this node is X, this node is Y, and this node is Z. We have named them. Now it is a rule to evaluate, that is the universal rule to evaluate the equivalent resistance of any network. You must start from the far end. You must start from the far end. That means if you want to calculate the resistance of this terminal, you need to start from far end. That means from here. That is the rule. Now with respect to, you see, if this is the node, if this is X, now if this is, let us say, Y, and let us say this is Z. Now just consider these two paths. One is this path and another one is this path. One along this 1 ohm and 5 ohm, and another one is 6 ohm. Now you see, if you consider this path, okay, if you consider this path, 1 ohm and 5 ohm. So basically you can find that these two resistances are connected in series. Why? Because same current is flowing through them. It is the same current. It is the same current is flowing through them. So basically this 1 ohm resistor and 5 ohm resistors are connected in series. So in the next diagram we replace these two resistances by a equivalent 6 ohm resistance. This is the first step. So equivalent resistance, that is RXZ, we have evaluated 1 ohm plus 5 ohm, that is 6 ohm. Okay. Now let us proceed. Again, if you consider 6 ohm, this 6 ohm and this 6 ohm, you can understand that they are two different paths with respect to X and Z. So if you consider this is X and this is Z, so we have two different paths, both having 6 ohm resistor. So one path is this, other path is this. So basically there are two parallel paths. So these two 6 ohm resistances are connected in series. Sorry, not in series. These two 6 ohm resistances are connected in parallel. This 6 ohm and this 6 ohm. So if two resistances are connected in parallel, so it will be 6 parallel 6. It will be 3. That means 6 into 6 by 6 plus 6, which is equal to 3 ohm. That means if two same value of resistance connected in parallel, the equivalent resistance is simply half. So it is 3 ohm. So it is exactly written by this 3 ohm resistance. So with respect to X and Z, it is simply, so these two 6 ohm resistances are replaced by an equivalent 3 ohm resistance. Now following to this, you can find out this 3 ohm resistance and this 2 ohm resistance should be in series. Moving forward, what is this? This 3 ohm resistance and this 2 ohm resistance are connected in series because same current is flowing. So basically this 3 ohm and 2 ohm are connected in series. So equivalently R, X, Z, Y. So this is X, this is Z, this is Y. So this is R, X, Z, Y, basically 3 ohm plus 2 ohm, it is 5 ohm. So now this 5 ohm resistance is replaced by this 2, 3 and 2 ohm. So this 3 and 2 ohm resistance is equivalently represented as 5 ohm resistance. And now again you see this 20 ohm. Now after reaching this node, it is looking relatively simpler. However, we can proceed further. Moving on, this 20 ohm resistance and this 5 ohm resistance are again parallel with respect to X and Y. With respect to X and Y, this 20 ohm and 5 ohm are parallel. So they are coming as a 4 ohm. Why? This 20 and 5 ohm parallel, that means 20 into 5 divided by 20 plus 5, which is 100 by 25 is equal to 4 ohm. So this 20 and 5 ohm parallel, it is equivalently represented as 4 ohm resistors across the terminal X and Y. Now moving on, now you see this 6 ohm resistance and this 4 ohm resistance again connected in series. This 6 ohm resistance and 4 ohm resistance are again connected in series because the same current will be flowing through them. So basically this 6 and 4 becomes 10 because they are connected in series. Now with respect to PQ, again you see 5 ohm and 10 ohm are in parallel. This 5 ohm and 10 ohm are in parallel. So 10 into 5 divided by 10 plus 5, it becomes 10 by 3 ohm. 50 by 15, that means it will become 10 by 3 ohm. So now it is 10 by 3 ohm. Now the final step, you can see this 1 ohm and 10 by 3 ohm, nothing in it, it is final step. So these two resistances are in series. So equivalent resistance across AB is the summation of these two because they are in series, 1 ohm plus 10 by 3. So it will be answering 13 by 3 ohm. So if you have a complex network like this, by reducing the network using the series combination and parallel combination, the R equivalent is found to be 13 by 3 ohm. So that means, what does it mean? If a resistance of this value 13 by 3 ohm you can represent across AB, it means same as like this big network. But remember one thing, you must start from the far end, from where you need to measure the resistance. You need to start far end from the measuring terminal. And step by step you should reduce your network using a series and parallel combination of resistances. Now let us proceed. Let us see the second problem. Now again, figure 15, we have another network. Now it is said that power consumed if the network shown in is connected to a 100 volt DC source. So let us say we have a 100 volt DC source. So if you have a network like this, what will be the total power consumption? That means again you need to bring this network into this form. This is 100 volt source and this is some equivalent resistance across AB. So let us say this is A. You see the positive terminal is connected across A and negative terminal is connected across B. So that is why I am telling this one as A and this one as B. So you need to measure something like RAB. So if you find out current, so what will be the current? Current is 100 by RAB. So then you can evaluate I square R is the power consumed. Now let us evaluate one by one how you can solve this. Now one thing, let us say this node is X, node is B, because it is next to this. Now you see, what do you mean by this symbol? It is directly short circuited. This line, this bold line, it means it is short circuited. Similarly for this also, this means short circuited. Now what does it mean short circuited? Now short circuit path is a path which provides zero resistance, so it provides actually zero resistance, so R becomes 0. So if a current flowing through the short circuit path I, then I into R becomes 0, that is voltage is 0. That means whatever voltage is here, that voltage appears at this point, because resistance is 0, no voltage drop is acting. So due to this fact, if this node is short circuited with some other node, so this X becomes this. That means this node itself appears at this node as it is, because resistance is same. And similarly, if these two nodes are same, the short circuited, then this B node is appearing as it is at this node, because it is a short circuit. So short circuit, that means 2 points are short circuit, means it is actually representing two nodes are same nodes, X, X. If this is X, this is also X. Short circuit means that. Now let us solve one by one. Now starting from here A, now from A to X, let us say this is X and A, we have a 2 ohm resistance, right? Now 3 9 ohm resistance, let us name them, mark them 1 2 3. 9 ohm resistance 1, 9 ohm resistance 2, 9 ohm resistance 3. Now from X, now this is X and this is B. Now from X to B we have a 9 ohm resistance 1. So from X to B we have a 9 ohm resistance 1. We have a 9 ohm resistance 2. So from B to X we have a 9 ohm resistance 2. Right? So again from X to B we have a 9 ohm resistance 3. Again from X to B we have a 9 ohm resistance 3. So this network apparently looks very complex. However, it is nothing but these 3 9 ohm resistance are connected in parallel. I repeat once again, from A to X we have 2 ohm. This is. Now from X to B, why this is B? Because this is short circuited with this node through this path. So this is B. So between X to B we have 9 ohm resistance marked with 1. So this is 1. X to B. Again from B to X we have a 9 ohm resistance marked with 2. Why this is X? Because it is short circuited with this path. So B to X it is 9 ohm resistance 2. B to X it is 9 ohm resistance 2. And again from X to B we have a 9 ohm resistance 3. So in this way these 3 resistances are coming parallel to each other. These 3 resistances are coming parallel to each other. So if we represent Same by a single resistance, basically 3 9 ohm resistance if connected in parallel, so it will be 1/3. So if we represent this network in this way, this is 100-volt source, we have this node as A. Now if we have a 2 ohm resistance and this is X and this is B, so what will be the resistance across XB? It is nothing but 3 ohm. Then from B to the negative terminal. So it is the supply source is 100 volt. This current is I. This is A. This node is A. So this is 2 ohm and this is 3 ohm. So 3 ohm is basically 3 9 ohms resistance connected in parallel. So it will be 9 ohm by 3. So they are connected in series. So across AB, so if you go back to this diagram, across AB it is 2 ohm and 3 ohm are connected in series. So basically it is 5 ohm. So that is the exactly thing that it is written. That is the equivalent resistance is 5 ohm. That is 2 ohm and 3 9 ohm resistances are in parallel. That is 5 ohm. So what will be current? Current is 100 volt by 5 ohm, which is equal to 20 ampere. So the power dissipation is I square R, which is current is 20 square and equivalent resistance is 5. So it will be 400 into 5, that is 2000 watt or 2 kilowatt. So the answer to this problem is the power consumption of this network is 2 kilowatt. So now moving to the next problem. It is a capacitance problem. Now figure 16, it is a parallel plate capacitor. A capacitor is formed by two parallel plates of area 5 centimeter square. So area becomes, it is given 5 centimeter square, separated by a distance of 1.5 centimeter. So distance is 1.5 centimeter. In air medium, so this medium is air. It is then connected to a 1000 volt DC supply. So this supply is actually 1000 volt. Now a flat sheet of dielectric material is introduced in the capacitor with thickness of 0.5 centimeter. So this represents actually that flat sheet, which is 0.5 centimeter. So evaluate the capacitance. What is given? The relative permittivity of the dielectric as 3. See, this is a series. So this sheet, of dielectric medium epsilon r is equal to 3, and also this sheet or air, these two dielectric mediums, these two will be connected in series. Simple. So the dielectric medium air will contributing a capacitance of C1 and it will be contributing a capacitance of C2. So this C1 and C2 connected in series. So what is C1? It will be the parallel plate capacitor is epsilon A by D. Now epsilon is epsilon 0 into epsilon r. What is epsilon 0? Epsilon 0 is 8.854 into 10 to the power minus 12 farad per meter. And epsilon r is 3 for this material and it is 1 for air. So that is why it is multiplied with 3. Now A, the area of the cross section is given 5 centimeter square. So you need to bring to the meter. So that means it should be multiplied with 5 into 10 to the power 4 meter square. So 5 into 10 to the power minus 4. Now what is the thickness? Thickness of the material is 0.5 centimeter. So 0.5 centimeter you need to multiply it with 10 to the power minus 2 to make it meter. So if you solve this equation, your capacitance of this added dielectric becomes 2.65 picofarad. 2.65 picofarad. Now coming to the air, the similar formula. Now in this case, instead of having 3, we have multiplied it with 1 because epsilon r is 1 for air. Epsilon r equal to 1 for air. Now the area of cross section is same. However, the distance now becomes 1.5 minus 0.5. Because due to the inclusion of this new material, now the gap distance of air becomes only this much, which is 1.5 minus 0.5, that is 1 centimeter. So that is why it is written 1 into 10 to the power minus 2. So now if you solve, you will get a capacitance of 0.44 picofarad. So you solve, two capacitances are in series, so it is the equivalent formula C1 C2 by C1 plus C2. So it is 2.65 into 0.44 divided by 2.65 plus 0.44. So equivalently you will get 0.377 picofarad. So if you consider this entire assembly or entire capacitance consisting of two material, it will contributing a capacitance of 0.377 picofarad. You see the unit is coming in picofarad, not in farad. Now moving on our last problem for this module, we have a inductance problem, right? Now it is given, this is a rectangular core as shown in figure 17. This is a rectangular core, this entire this thing. So entire this thing is a rectangular core. Iron core rather is shaded by yellow, and this little gap is a air gap. This little gap shaded by, let us say by green, let us use some other color. So this little gap, it is air gap of 5 millimeter thickness. So this is made up of iron, which is having relative permeability is equal to 1400, and this is air gap, which is having relative permeability is 1. So its mean length of magnetic path is 100 centimeter. So this entire thing is 100 centimeter, is given by this 100 centimeter, and the cross sectional area is 4 centimeter. So this length is the mean length is 100 centimeter, and cross sectional area becomes 4 centimeter square, or you can say this is 4 into 10 to the power minus 4 meter square. Now there are 3 coils. There are 3 coils. The 3 currents are flowing, I1, this is I3, and this is I2. And we have a number of turns as mentioned. N1 is equal to 335, N2 is equal to 600, and N3 is equal to 600. So we have 3 coilings on a same iron material. Now the current flowing in each coil is represented by I1 is 1.6 ampere, I2 is 4 ampere, and I3 is 3 ampere. Now you need to evaluate the flux. Now if you have only one coil, it is very easy to calculate. However, you have 3 currents. Now 3 currents I1, I2, I3, it will create or it will induce its own magnetic field. Now you can see, if you consider the first one, so you see the current is flowing in and it is flowing in clockwise direction. So clockwise direction means, so if you recall, so clockwise direction means the magnetic field will be directed along the thumb rule. So that is why the magnetic field created by I1 is directed by this arrow. Okay. Now if you consider I2, the current flowing is in which direction? Anti-clockwise direction, right? Sorry, current not flowing in the anti-clockwise direction, current flowing in the clockwise direction, because this is the direction of the current. So current is flowing in this direction. So same direction, it is the clockwise direction. So with respect to I1, it is same. The direction of the magnetic field will be directed along this direction. Now if you consider the current 3, the current 3 will be directed, it's flowing in this way. So what is the direction? Again, it is an anti-clockwise direction, so magnetic field will be in this way. The same thing. So now you see the magnetic field created by I1 and I3 will be acting in the same direction. However, magnetic field created by I2 is opposing in the different direction, opposite direction. So this is I1 and I1 and I3, but this is I2. So the net magnetic field, okay. So now what will be the MMF due to current 1? So let us consider MMF 1. MMF 1 is equal to 335 into 1.6. MMF 2 or MMF 3 rather, this current I3, it will be 600 into 3, because 600 number of turn, current is 3. So 600 into 3. And what is MMF 2? That is due to the current I2, it will be 600 into I2 is 4. So it will be 2400 ampere turn. It will be 800 ampere turn, 1800 ampere turn, and it will be coming out to be 335 into 1.6. It will be coming out to be 536. 536 ampere turn. So if you add these two, because you see these two are additive, because they will be acting in the same direction. So if this to be added, then all together they will give you mmf1 plus mmf3, they will give you 2336 ampere turn. So mmf1 and mmf3 altogether gives you 2336. So in this direction it is 2336 ampere turn. 2336 ampere turn. However, due to this magnetic field created by current I2, it is 2400. So the net MMF is equal to 2400 minus 2336, which is equal to 64 ampere turn, and which is directed along this direction. Okay, so direction of the net field is this. This is the direction of the net field, which is 64 ampere turn. Now moving on. Now reluctance of iron. We have this formula. What is the reluctance formula? Well known formula to us. It is 1 by mu naught mu r into L by A. Now you know mu naught mu r. Mu naught is 4 pi into 10 to the power minus 7. I have already mentioned this value, mu naught. This is mu naught. Mu r is 1400. It is given of iron. And now it is the mean length is 100 centimeter. However, this 100 centimeter, so from there mean length of iron is how much? Mean length of iron is 100 centimeter. Now you need to subtract this much, 5 millimeter. You need to subtract this much, 5 millimeter, which is coming out to be 0.995 meter. And area of the cross section 4 into 10 to the power minus 4 meter square. That is exactly written. So now if you solve this, you will get this value, 5.6 into 10 to the power 6 ampere turn per Weber. Similarly, if you calculate air gap reluctance, so air gap reluctance is same thing, 1 by 4 pi 10 to the power minus 7. Now it is 1, mu r is 1. Now the gap 5 millimeter is for air, air is 5 millimeter, which is equal to 0.005 meter, and the cross sectional area remains same. So if you solve this, you will get 9.95 into 10 to the power 6 ampere turn per Weber. So basically this is a series magnetic circuit. So the net reluctance or total reluctance is the reluctance of iron and air summation. So if you add these two, you will get 15.55 into 10 to the power 6 ampere turn per Weber. So from the Ohm's law applied in magnetic circuit, so flux, that is net MMF divided by net reluctance. What is net MMF? It is 64, and net reluctance, it is 15.55 into 10 to the power 6. So if you calculate, this will be coming out to be 4.12 micro Weber. The direction of the flux in this direction. Flux should be flowing through this. So this is the problem. So with this, I am ending here. So this is all about the module 1. So we have briefly discussed the preliminary ideas of resistance, inductance, capacitance, and thereon we have discussed some familiar term related to the networks, and we have seen some problems on resistance, inductance, and capacitance. Thank you.